Radioactivity or radioactive decay is the process through which the nucleus of an unstable atom loses energy by emitting nuclear particles or ionizing radiation. Henri Becquerel, a French physicist and chemist, is credited with the discovery of radiation on March 2, 1896. But let's roll back the clock a few months and describe the preceding events leading up to this now auspicious day in physics history. X-rays were discovered on November 8, 1895 by Professor Wilhelm Conrad Roentgen while working on a device called a Crookes tube in his first floor laboratory at the University of Würzburg in Würzburg, Germany. Over the following few weeks, Roentgen quietly evaluated the properties of his newly discovered rays, which he labeled X for the algebraic symbol of the unknown. Soon after Christmas of 1895, on December 28th, Roentgen submitted his first provisional communication in the Proceedings of the Würzburg Physico-Medical Society in an article entitled On a New Kind of Rays, and gave his first and only public presentation of his discovery to the members of the same society soon after the New Year's of 1896. At that demonstration, Roentgen took this radiograph of the famed German anatomist Albert von Kolliker's right hand, who immediately lauded the new discovery as revolutionary and proposed the new rays be labeled Roentgen rays in honor of their discoverer. News of this mysterious new ray that could pass through solid objects quickly circulated around the world. In fact, the first medical radiograph was performed at Dartmouth College on January 19, 1896, only a few weeks after Roentgen's announcement. In early 1896, scientists were aware of the phenomenon of phosphorescence in certain salts of uranium, whereby the rock mineral would give off visible light in a darkened room for minutes to hours after exposing the stone to sunlight. Professor Becquerel, working with a crystalline crust of the phosphorescent material potassium uranyl sulfate, suggested that, in addition to the familiar visible phosphorescence, that these substances could possibly emit some of the mysterious new penetrating rays described by Roentgen a few months earlier. To test his hypothesis, Becquerel wrapped a photographic plate coated with a silver bromide emulsion in 2 sheets of very thick black paper to prevent fogging from direct sunlight. He then placed slabs of the uranium salt on top of the black paper, some directly on the paper, and others on a piece of money or metal screen. The entire apparatus was then placed in the sun for several hours. Developing the photographic plate, Becquerel identified the silhouette of the stones in black with the metallic objects like this Maltese cross appearing in the negative. Becquerel described his findings to the French Academy of Science on 24 February 1896, concluding that, from these experiments, it is evident that the phosphorescent substance in question emits rays which pass through the opaque paper and reduce silver salts. At this point, Becquerel was certain that the observed phenomenon was the result of the uranium crystal's ability to absorb energy from the sun and re-emit that energy in the form of the identified penetrating rays. However, further investigations and a fortuitous streak of bad weather on the last few days of February 1896 caused him to abandon that hypothesis. A few days after his presentation to the French Academy, on the 26th and 27th of February 1896, Becquerel prepared his experiment as before with a photographic plate coated with silver bromide emulsion and covered in the 2 thick sheets of black paper. He placed the potassium uranyl sulfate crystals on the plates, some directly on the black paper, and others on top of various metallic objects. Since the skies were overcast, he placed the entire apparatus in a desk drawer where it sat for the next 3 days. On that day, He developed the photographic plate, expecting at most a faint shadow from the phosphorescent stones. To his surprise, the silhouettes appeared with great intensity. He immediately reported his findings to the French Academy of Science, suggesting that the observed phenomenon may be intrinsic to the uranium salt itself and independent of the phosphorescent effect. By May of 1896, after a number of experiments with non-phosphorescent salts of uranium, he arrived at the correct explanation that the penetrating rays were emitted spontaneously from the uranium mineral without the need for an external source of energy or excitation by the sun. These became known as uranium rays. Maria Skłodowska-Curie, a native of the Kingdom of Poland in the Russian Empire, was a 28-year-old graduate student of physics and math pursuing research on the magnetic properties of steel in her husband Pierre's laboratory at the Paris Municipal School of Industrial Physics and Chemistry when Becquerel announced his findings on uranium rays in 1896. Soon after the birth of their first daughter Irene in September of 1897, Marie began looking for a research topic to pursue her doctoral degree in science. Familiar with Becquerel's discovery of uranium waves almost a year prior, she felt this would be a topic worthy of investigation as there was so little existing research to review. As fate would have it, Marie's husband, of just over 2 years, was already a well-known scientist in Paris, as he and his brother Jacques, shown here with their mother and father, had discovered the piezoelectric effect 17 years earlier. They demonstrated that, when certain crystals like quartz or Rochelle salt were deformed or compressed, the mechanical strain produced an electrical potential. They subsequently discovered the converse was also true, causing the crystals to deform or compress when placed in an electric field. In fact, they noticed that compressing the crystal would produce a potential, positive on one side and negative on the other, and that stretching the crystal would produce the opposite polarity. The brothers immediately put their discovery to practical use by inventing several pieces of sensitive laboratory equipment like this piezoelectric balance, capable of accurately measuring small quantities of material. Now, in 1880, the brothers would not have had access to a modern-day voltmeter to carry out their experiments on the piezoelectric effect. At that time, the only instrument capable of accurately measuring electrical potential was an ingenious device called a quadrant electrometer developed by Sir William Thomson or Lord Kelvin in 1857. The instrument consisted of a central torsion wire electrically isolated from the housing with 4 additional electrically isolated terminals, each of which communicated with one of 4 metallic plates suspended in the housing chamber. Just above the 4 plates, a metallic dumbbell-shaped vane was solidly affixed to the torsion wire. Below the plates, and similarly affixed to the torsion wire, was a reflective mirror. Depending on the nature of the experiment, various wiring configurations could be utilized with the electrometer. Most commonly, the diagonal plates were electrically connected, and the output leads from the test device were then connected to each of the diagonals as shown. Finally, the lead to the torsion wire was connected to a voltage source such as a Leyden jar, precursor of the modern-day capacitor, or, as shown here, a voltaic pile or prototype battery, which consisted of alternating plates of copper and zinc separated by cardboard discs soaked in salt water. The pile provided a positive charge on the torsion wire and dumbbell-shaped vane. As we weight the scale, the tension on the quartz crystal again produced a voltage potential, positive on one side and negative on the other, the strength of which is proportional to the amount of weight. The positive lead from the scale provides a positive charge to 2 of the 4 plates across the diagonal, and the negative lead puts a negative charge on the remaining 2 plates across the diagonal. Remembering that opposite charges attract and like charges repel,
This configuration causes the tension wire to rotate as the vane is pushed away from the positive plates and pulled towards the negative plates. The reflective mirror rotates with the vane and wire and reflects a small light onto a scale board. The heavier the weight, the more rotation and the farther the light moves along the scale. Similar equipment, with some modifications, was instrumental in Marie's work in the subsequent discovery of the radioactive elements polonium and radium nearly 2 decades later. Details of Marie's laboratory setup are surprisingly limited, and some of the descriptions I found are contradictory or nonsensical. This may be due to the fact that her notebook and many of her personal items are so radioactive that they are kept in lead-lined boxes in the National Library in France, so access is limited. The quadrant electrometer shown in the animation was probably not sensitive enough to carry out the Curie's work. This model, with the vane enclosed in a hollow cylindrical tube cut into quadrants, was likely the instrument of choice. For demonstration purposes, we'll continue to use the earlier model, however. The electrometer requires some rewiring as well. We're going to switch the leads, placing the positive on the front terminal and the negative on the back. We'll also remove the diagonal electrical connections on the terminals. This configuration applies a positive charge to the front right plate and a negative charge to the right rear plate, causing the vane, armature, and mirror to rotate rightward towards zero. If we place enough weight on the scale, we can move the reflected light all the way to the left. The process is similar to a more modern-day voltmeter where you select your range or scale of voltages and use a small potentiometer to move the needle to the zero mark. In this picture, we can see Marie, quote, setting her scale. The remaining 2 terminals on the electrometer were then connected to a device best described as a prototype ionizing chamber that Marie designed to evaluate the newly discovered uranium waves. The apparatus consisted of 2 parallel plate condensers, 8 centimeters in diameter, and separated by a distance of 3 centimeters. A 100-volt DC electrical supply, depicted as a voltaic pile in this animation, was then connected in series to the electrometer and the condenser plates. The positive pole of the voltage source was connected to the front left terminal of the electrometer, and the negative pole was connected to the back left pole through the condenser plates. Ordinarily, air is an insulator to electrical currents at low voltages. With nothing on the condenser plates, the current reading was 0. However, Marie noticed that when one of the plates was covered with a finely pulverized uniform layer of uranium salt, the air gap became conductive and a measurable current flowed between the plates.
As indicated by the opposite rotation of the vane, torsion wire, and mirror, with subsequent movement of the reflected light up the scale.
She then set out to evaluate other substances that were capable of increasing the local conductance of air. Marie found that various compounds of uranium produce currents of 18 to 24 times 10 to the minus 12 amperes, or 18 to 24 picoamperes, while a thick 6 mm layer of the substance thorium produced currents of 53 picoamperes. The most impressive results were obtained from a substance called pitchblende, which increased the air conductance 3 to 4 times that of the uranium compounds with measured currents of up to 83 picoamperes.
About a decade earlier, in 1887, Heinrich Hertz produced radio waves in his laboratory in Bonn, Germany.
These waves were capable of carrying a signal through space and producing an assumed action at a distance where information or energy was transferred from one area to another without a direct physical connection. Marie assumed that the effect of uranium waves on the conductivity of air between the condenser plates was similar to the action of radio waves, and thus coined the term radioactivity to describe the observed phenomenon. Marie correctly postulated that the intense radioactivity of the pulverized pitchblende could not be explained by the uranium content itself, and therefore other active elements were likely present in the mineral. She and her husband began a systematic search to isolate these elements, finding initial success in July 1898 with the announcement of a new radioactive element, polonium, named after Marie's homeland, Poland. On 26 December of 1898, the Curies announced the discovery of their second isolated radioactive element, which they named radium after the Latin word for ray. In 1899, within 1 year of the Curies announcing their discovery of the new element radium, Ernest Rutherford, the father of nuclear physics, also working with uranium minerals, announced his discovery of two different types of radioactivity that seemed to differ in their penetrating power when compared to the previously discovered X-rays. The first of these radiations, which he labeled alpha, were blocked by a sheet of paper. The second, labeled beta, passed through the paper but were blocked by a thin sheet of metal foil. The radiation that passed through the paper and the foil initially remained unnamed. Subsequent studies by Rutherford and others showed that the previously labeled alpha radiation moved relatively slowly and exhibited a small deflection in electric field towards the negative polarity. Beta radiation, on the other hand, moved much faster and showed a large deflection to the positive pole of the same electric field. A year later, in 1900, the French physicist and chemist Paul Villard described the remaining rays, reiterating their ability to penetrate thick sheets of metal and showing no deflection in an electric or magnetic field. Rutherford eventually named these rays gamma in 1903. Rutherford's investigations over the next decade on radiation and matter led him to the now generally accepted conclusion in 1911 that atoms consisted of a small, positively charged nuclei surrounded by a large empty space encircled by tiny, negatively charged electrons. In collaboration with Frederick Soddy, he was the first to correctly suggest that radioactive phenomenon was an atomic process due to the spontaneous disintegration of the atom and transmutation of elements into completely new substances. The two also suggested the phenomenon of a radioactive half-life, where half of a given radioactive parent isotope will transmute or decay into its daughter nuclei in a fixed and reproducible time period, regardless of the original size of the sample. Just after World War I, Rutherford is credited with the discovery of the proton and, at the same time, suggested the existence of the neutron, the two components of all atomic nuclei. Rutherford's model of the atom, along with other theories like general relativity, now provide us with an accurate and relatively simplistic explanation of all radioactive phenomenon. This apparatus is designed to explain the concept of ionizing radiation. A high-voltage power source provides a 300,000 volt potential at the two sets of terminals which are connected in parallel. The rear terminals are a fixed distance apart, and the front terminal distance is adjustable. The front terminals are also situated under a radiation source, a standard medical fluoroscope. In fact, this is the radiographic image of the front terminals. Ordinarily, air is a poor conductor of electricity. However, a spark will jump an air gap if the terminals are close enough and the voltage is sufficient to push the electrons across the gap. In addition, the spark will take the path of least resistance, so if the front terminals are closer together than the rear, the spark jumps across the front terminals. If we then move the front terminals apart,
until their distance just exceeds that of the rear terminals. The spark now jumps the rear gap. Now, if we turn on our fluoroscope and maintain the front terminal distance, the spark moves from the rear fixed terminals to the front terminals even though they are further apart. When we turn the radiation source off, the spark again takes the path of least resistance to the rear terminals. This demonstrates the phenomenon of ionizing radiation. When the X-rays, a form of ionizing radiation similar to gamma rays, pass through the air gap between the front terminals, they can knock away some of the orbiting electrons around the nuclei of the oxygen, nitrogen, and other gases in the air, turning neutral atoms into positively charged ions. These ions reduce the electrical resistance between the larger gap and allow a spark to jump across the terminals. This is the same phenomenon Madame Curie noted in her 1897 and 1898 experiments describing the increased conductivity of air produced by uranium waves. As suggested by Rutherford, the atom consists of a central nucleus containing a mixture of the subatomic particles, the positively charged protons, and the neutral neutrons. Encircling the nucleus are the negatively charged electrons. The relative mass of these subatomic particles are as follows. Neutron, 1. Proton, 99.86% of the neutron. Electron, 0.054% of the neutron. As you can see, most of the atomic mass of the element is attributable to the protons and neutrons in the nucleus, with a negligible contribution from the encircling electrons. When we look at an element on the periodic table, the central letter represents the chemical symbol or abbreviation, in this case, the basic building block of all life on Earth, the carbon atom. We'll explode out the nucleus slightly so we can easily count the components. The upper number above the chemical symbol describes the number of protons in the nucleus and is called the atomic number. The lower number is the atomic mass and accounts for the total mass of the atom, including all the protons and neutrons in the nucleus and, in certain tables, the minuscule contribution from the encircling electrons. The chemical behavior of an element is determined by the number of encircling electrons, and to maintain electrical neutrality, there are always the same number of protons in the nucleus as there are orbiting electrons. Therefore, the chemical identity is determined solely by the atomic number. Increasing or decreasing the number of neutrons in the nucleus creates isotopes of that element and changes the atomic mass but does not affect the chemical behavior. For instance, if we add 2 neutrons to the nucleus of the carbon atom, the atomic number remains unchanged at 6, but the atomic mass increases by 2 to 14. Some may recognize carbon-14 as the unstable isotope of the carbon atom used in carbon dating of ancient archaeologic and geologic artifacts. With a half-life of approximately 5,730 years, this methodology can be used to determine the age of artifacts up to approximately 50,000 years old. Some isotopes are stable and some are unstable. The unstable variety can decay or transmute into different elements that themselves may be stable or unstable. With enough time, all unstable isotopes will eventually transmute into stable elements through a decay chain as shown here with uranium-238, eventually becoming the stable element lead over billions of years. A variety of nuclear decay processes exist, but we will discuss the 3 most common in one special situation. It may be useful to pause the video at this point and print out a copy of the periodic table to use as a guide for the following discussion. Using our carbon-14 isotope, we've already determined that we have too many neutrons when compared to our stable carbon-12 nucleus. This particular isotope decays by one of the neutrons, giving off a small, negatively charged particle or electron, just like the electrons encircling the nucleus, and leaving behind a proton. In addition, to account for an apparent loss of momentum and energy in the transformation, a theorized small neutral particle called an antineutrino is also released. The neutrino and its antiparticle, the antineutrino, were named by the Italian physicist Enrico Fermi in 1933 and literally translates as little neutral one. The negative electron that is given off would of course move toward the positive pole of an electric field and corresponds exactly to the beta-type radiation described by Rutherford in 1899. Therefore, this type of decay is referred to as beta decay. More specifically, this is beta minus decay since the small electron released is negatively charged. You'll see why we make this distinction in a moment. If we look at our chemical placard, our carbon atom has now lost one neutron and gained one proton. Therefore, our atomic number goes up by 1 and our atomic mass is basically unchanged. Looking at our periodic table, the element corresponding to this configuration is nitrogen and is stable. Therefore, carbon-14 transmutes to stable nitrogen through beta minus decay with a half-life of 5,730 years. For the remaining nuclear decay processes, we will again use our carbon-14 atom, but understand that this is for demonstration purposes only. Carbon-14 does not decay by any other means except beta minus as described above. Let's say our nucleus has too many protons and neutrons. These unstable atoms can give off a set of 2 protons and 2 neutrons, which is the same as a helium nucleus. This bulky particle with 4 subatomic units, including 2 positively charged protons, would move relatively slowly and show deflection towards the negative pole of our electric field, corresponding to the alpha radiation described by Rutherford in 1899. Therefore, this is referred to as alpha decay. This decay reduces our atomic number by 2 and reduces our atomic mass by 4. In our example, remembering that the atomic number determines the chemical behavior, our atom becomes beryllium-10, a known isotope of the stable element beryllium-9, with a half-life of 1.39 million years. An example of actual alpha decay is radium-226, first isolated by the Curies in 1898. After giving up its helium nucleus of 2 protons and 2 neutrons, the new element is the radioactive gas radon-222 with a half-life of 3.8 days. This too undergoes alpha decay to produce polonium-218, an isotope of polonium-210, the other element discovered by the Curies in mid-1898. As these elements transmute, there is matter and energy shifting around inside the nucleus, with neutrons turning into protons and vice versa. Occasionally, there is some excess energy left over after these transformations that the atom needs to expel. This energy is dissipated in the form of an electromagnetic wave with penetrating properties similar to X-rays. The waves are electrically neutral and therefore are not deflected in an electric field. These waves correspond to the gamma radiation discovered by Villard in 1900 and named by Rutherford in 1903. Therefore, this type of decay process is named gamma decay. Since the contents of the atom itself are unaltered, the atomic number and the atomic mass remain the same. We usually denote the parent atom with a small letter m after the atomic mass, which stands for metastable, indicating the excess energy content of the nucleus. The most familiar element in this category is technetium, the workhorse of medical nuclear imaging. With a half-life of 6 hours and essentially pure gamma radiation production, this particular element is well suited to evaluate various physiologic processes in the body, such as gastric emptying, gallbladder function, and gastrointestinal bleeding. The last decay processes deal with unstable isotopes with too many protons in the nucleus. There are actually 2 types of decay that facilitate this transformation depending on the energy differential between the parent and daughter nuclei. If there is sufficient energy available, one of the protons is converted to a neutron by giving off a small, positively charged particle with a mass identical to the electron, but with the opposite charge. This is called a positron and actually represents the antimatter equivalent of the electron. The proton also gives up a neutrino. the antimatter equivalent of the antineutrino, to account for the apparent loss of momentum and energy as seen in beta minus decay. This antimatter positron leaves the nucleus but doesn't travel far before it encounters one of its negatively charged cousins in the electron cloud encircling the nucleus itself. The particle and the antiparticle collide, annihilate one another, and convert all their mass into pure energy, producing two identical 511 kiloelectron volt X-rays which propagate away from one another 180 degrees apart. These rays can be picked up by a specialized PET or positron emission tomography camera to produce PET images of the body. This conversion drops the atomic number by 1, but keeps the atomic mass essentially unchanged. An example of this type of decay is the fluorine isotope F18, which transmutes to the oxygen isotope O18 through beta plus decay and is one of the common elements used in PET imaging via the agent FDG, or fluorodeoxyglucose. For those paying attention, you may notice that this particular transformation appears to create mass out of thin air. Remember that the neutron, of course, has an atomic mass number of 100% of the neutron, the proton 99.86% of the neutron, and the electron and positron 0.054% of the neutron. From a mass standpoint, converting the proton to a neutron and giving off a positron and a neutrino doesn't seem possible. However, as the nucleus becomes more stable, some of the binding energy of the protons and neutrons is converted to mass according to Einstein's equation E = mc squared, and can make up for the apparent deficit. Not to get into too much confusing detail, but I do think a brief discussion of elemental atomic particles is warranted to explain the phenomenon. The ancient Greeks called the smallest indivisible element of matter, such as this rock fragment, an atom. In fact, the Greek word for indivisible was atomos. Since Rutherford, we now know that atoms are made up of smaller elements called subatomic particles, the proton and the neutron. Modern atomic theory states that the proton and neutron are made up of even smaller elemental or fundamental particles, so called because they are truly indivisible and are the fundamental structures linking energy and matter. These structures include quarks and gluons, as well as the orbiting electron itself. Quarks are the smallest known particles to exhibit measurable mass, whereas the massless gluons are apparently pure energy and, as the name implies, are the forces that hold or glue the fundamental particles together to create protons and neutrons. Quarks come in 6 types or flavors, including the first generation up and down, second generation charm and strange, and third generation top and bottom. The upper quarks all have an unusual charge of plus 2/3, and the lower quarks all have the equally unusual charge of minus 1/3. The absolute mass of the particles in megaelectron volts is shown below each particle. In nature, the only 2 quarks that are found in abundance and are the basic building blocks of the neutron and proton are the up and down flavors, so we'll ignore the other types for now. We will represent the up and down quarks graphically with arrows as shown. Note that the down quark has more than twice the mass of the up quark, which will be important when we talk about the relative masses of the proton and neutron in a moment. Each subatomic particle is made up of 3 quarks held together by 3 gluons. In a proton, there are 2 up quarks and 1 down quark. Adding up the individual charges of the fundamental particles, this configuration provides a net charge of plus 1, hence the positively charged proton.
On the other hand, the neutron is made up of one up quark and two down quarks. Adding up the charges of the fundamental particles, this configuration provides a net charge of 0, hence the neutral neutron. Remember also that the addition of a down quark provides extra mass to the neutron and at least partially accounts for the mass differential between the proton and neutron. Interestingly, however, the quarks only make up about 2% of the total measured mass of the protons and neutrons. The remaining 98% appear to arise from the pure energy massless gluons holding the quarks together. The gluons, therefore, may be the link between energy and matter as predicted in Einstein's famous equation. In summary, the apparent mass deficit in beta-positive decay shouldn't bother you, as the process likely involves some mass generation from the excess energy produced as the nucleus decays to a more stable state. For isotopes with excessive protons but insufficient energy to undergo beta-positive decay or positron emission, an alternative mechanism is available called electron capture. In this decay process, the nucleus captures an inner shell orbiting electron, which is absorbed by the excess proton. The proton is converted to a neutron, and the nucleus emits a neutrino. In addition, one of the outer shell orbiting electrons then falls into the vacant inner shell and gives up energy in the form of an electromagnetic wave. Remember that the only difference between an X-ray and gamma ray is where they are produced. Gamma rays are produced in the nucleus of the atom as it gives off excess energy. X-rays, on the other hand, are produced in the electron cloud. Therefore, electron capture actually produces X-rays as the outer shell electron falls into the inner orbit. Similar to positron emission, the atomic number decreases by 1, but the atomic mass remains unchanged. A clinical example is thallium-201, which decays to mercury-201 and produces mercury X-rays of about 70 to 80 kiloelectron volts, which can be used in cardiac imaging. In summary, nuclei with excess protons and neutrons undergo alpha decay, reducing their atomic number by 2 and atomic mass by 4. Nuclei with excess neutrons alone undergo beta-minus decay, converting a neutron to a proton and increasing their atomic number by 1 while leaving the atomic mass unchanged. Nuclei with excess protons alone and a sufficient energy differential between the parent and daughter nuclei undergo beta-positive decay, converting a proton to a neutron, decreasing the atomic number by 1 while leaving the atomic mass unchanged. Isotopes with insufficient energy differential between the parent and daughter nuclei can undergo electron capture with the same result. Finally, nuclei with excess energy alone undergo gamma decay, producing gamma rays while leaving the atomic number and atomic mass unchanged.